pretty much said there's only two techniques really: substitution and parts. So let's look at this idea of parts. So when we use it is when we've got a product of two functions. You could kind of think of it like a product rule for integration. And in fact, that's where we get it from. Here's the formula. The integral of u to v is uv minus the integral of v to u. But as I say, it actually comes from the product rule. So if I write down our product rule, so differentiate uv, u and v being two different functions, write down the first, diff the second, plus write down the second, diff the first. If I integrate both sides, well, the left-hand side just becomes uv. The right-hand side, I'm now splitting that up into two integrals. The dx's will cancel, if you like, rearrange it, and we get this formula. The integral of u to v is uv minus the integral of v to u. So we're going to be integrating two functions. One of those functions will be u, the other function will be dv. Now, how do I choose which function is which? U. Well, I want to choose it so that when I differentiate it, I get a simpler function to work with. That's the idea. The dv, well, because I'm going to have to go backwards and work out what v is, I got to choose something that can be integrated. Because if I can't integrate it, well, then it's no good for dv. All right, so that's the idea. Let's look at some. So integral of x sine x. There's no way I could create derivative times function here. Because I've got x, I've got sine x. So we'll do it by parts. I'm going to choose u to be x, because if I differentiate x, I get 1. That's a lot simpler. Whereas if I differentiate sine x, I'll get cos x. Well, it's pretty much the same thing. U is going to be x, which means du is dx. Dv is sine x, so go back to get v, integrate sine, I get minus cos. uv, x times negative cos x, minus v to u, so minus cos becomes plus cos. I can integrate cos, that's no issue, and we get our answer. I put the positive thing at the front, but there it is, sine x minus x cos x. The integral of log x, and you recall I've been saying, oh, just remember it's x log x minus x. Well, this is where it comes from. But it looks like I've only got one function there. Actually, I've got two functions there. It's just that one of those functions is the number 1. So anytime I've got a difficult thing to integrate, even though it's just one function, I can still do it by parts and say, oh, well, the other function is just 1. Let's see what happens. I'm going to choose u to be log x. Now you might think, well, hang on, if you choose u to be 1, differentiate it, you get 0. Surely that's easier. But remember the other criteria. If I choose u to be 1, then dv's got to be log x, and dv had to be something I can integrate. Well, that's my problem anyway. So in this case, u will be log x, du becomes dx on x. That means dv is just the dx, v becomes x. So uv, x log x, minus the integral, well, when we multiply v to u together, the x's cancel. I'm just integrating dx, which is x. And so that's where it comes from. There's our x log x minus x. Let's do a definite one. xe to the power of minus 7x. Again, I can't create the derivative times function here. I'm going to choose u to be x, because if I chose u to be e to the minus 7x, well, remember when we differentiate exponentials, the power doesn't change, so I'm going to keep getting some multiple of e to the minus 7x. It's not going to become simpler. The u will become dx, the v will be the e to the minus 7x, integrate that, I've got minus 1/7 e to the minus 7x. uv, now, this is a definite integral, so the uv goes in the brackets, plus 1/7, 0 to 1, e to the minus 7x. It's up to you whether you want to substitute those numbers in now or just leave the substitution right to the very end. I tend to do it that way, unless they're easy numbers. But when I integrate the other bit, I now get minus 1/49 e to the minus 7x. Now let's substitute in the 1, substitute in the 0, and we have our final answer. This one's interesting. E to the x cos x. Choose u so that when I differentiate it becomes simpler. Well, if I choose e to the x, I differentiate it becomes e to the x. No, that's not simpler. If I choose cos x, differentiate it, I get minus sine x. Well, that's not simpler. Maybe I'll look at the other criteria. dv, something I can integrate. E to the x. Oh yeah, I can integrate that. That's reasonable. Cos x. Well, yeah, I can integrate that. So it really doesn't matter with this one which way I go. Which way did I go? I went u equals e to the x. Du is e to the x dx, that means dv is cos x, integrate cos, I get sine, we get uv, e to the x sine x, minus v du. Pretty much the same problem I originally had. So we do it again. But here's the thing, when you do it again, you need to go with the same choice that you made. If I was to now all of a sudden say, oh look, I'll make u equals sine x, I'll end up back where I started from and get some argument like 0 equals 0 or something like that. Alright, I'll stick with my original decision. U is e to the x, du is e to the x dx, dv becomes sine x, v is minus cos x. Okay, minus uv, well uv is minus e to the x cos x, so minus becomes a plus. Oh my goodness, we're back to where we started from. But now I look at this and I don't see it as lines working out, I see it as an equation. That minus the integral of e to the x cos x, I can move to the left hand side. And I now know that 2 times the integral of e to the x cos x dx is e to the x sine x plus e to the x cos x. Divide by 2, I have my answer. Now some people look at this and they think, well hang on, we haven't actually done any integration. Well yeah, we have. It was over on the right hand side. We did all the integration, working out there. So we have integrated, but there's our answer. So let's play with this idea of integrating by parts.